Welcome, everyone. Today's conversation is going to be on the foundations of physics, issues of quantum mechanics, the measurement problem, entanglement, non-locality, things of that sort. And I'm so pleased that we have Tim Maudlin, who's a professor of philosophy at NYU, also the founder and director of the John Bell Institute. John Bell, a name that those of you who have done some reading on the foundations know as a towering figure in that field, no doubt a name that will come up in our conversation. So welcome, Tim. So
good to
nice
be here.
to have you. So let me just jump in with my own experience of some of the issues that you have spent your life thinking about. I was a young faculty member at Cornell in the 1990s, I guess. And I went to this colloquium by David Merman.
Mm-hmm.
And he did this beautiful job of explaining, what Bell had put forward and what the experiments had shown and so forth. And I was sitting there and I said to myself, I'm a professor. I teach some of this stuff, but I'd never really appreciated things at that point until I was really, privy to this wonderful explanation by David Merman. Is that a common thing that you find in terms of people's knowledge of the insights?
Yeah, I mean, I can give you a data point before yours and a data point after yours. So before yours is my own. When I was an undergraduate in 1979, I read a Scientific American article by Bernard Despaignat, which maybe you're too young for that. It had a big dung beetle on the cover. And that was the first time I'd heard of Bell's work. When I look back at that article, it has its problems, but it got enough of it across to me that I became extremely worried, or I don't know how to describe it. I was pacing. My roommate saw me pacing in circles reading this thing with my brow furrowed. I understood it was a very, very profound and surprising result. Now that's, of course, long after it was published. And then I can give you another data point from last year. I gave a talk on Bell's theorem and relativity at Johns Hopkins for a general audience, and a guy in the audience put up his hand. He said, I have a PhD in astrophysics. I've never heard of any of this. He was completely unfamiliar. He said, why didn't they tell me?
Right.
So yeah, I think it's a very strange history that Bell's work, which is so remarkably clean, logically clean, sharp, it kind of got buried. And a lot of physicists completely misunderstand what he proved.
Right. So I'd love to get into that, but maybe we can walk through a little bit of the history. And the reason I want to do that is not so much to give just historical context for its own sake, but rather they're key people in the history of quantum mechanics that, at least as I read the history, and I'd be interested to hear your perspective, they set thinking, even from a sociological point of view, in a direction that I think perhaps explains, at least in part, why these experiences, my own and the two that you just recounted, are not that uncommon. And I think a person who played a key part, who had a profound impact on our deep understanding. So this is not a general criticism, but Niels Bohr had this perspective that, look, what are you supposed to do as a physicist? You're supposed to explain the numbers that come out on our readouts, on our detectors. And once you can explain those numbers, you're done. There's no need to kind of be able to tell the actual story of what's going on. That's not what physics is about. Is that your reading of what he was trying to say?
Well, it's a curious word you used there, which was explain. Because
I should take that back.
Right.
Yes.
Because
right.
I mean, I don't think this was exactly Bohr's attitude.
Right.
The common attitude,
if you could predict it,
is calculate,
yes.
predict.
Better
right?
way
Just
of
tell
saying
me
it.
what the numbers will be, and if the numbers are right, that's all I want.
Absolutely.
Bohr was actually trying to make a much more profound argument, which was that a certain sort of explanation which had been provided by classical physics was no longer available, just could not be found. There wasn't, that nature didn't provide the kind of explanation we're used to. I think there's a very deep background here going into Kant and neo-Kantianism, but I don't want to bore you with that. But certainly, Bohr used some words he seemed to have gotten out of Kant about visualizability. So he sort of had this idea that we've reached a point where we can't visualize the subatomic world. One might respond, fine, I don't care if I can visualize it, but there's more to, there are explanations you could give that wouldn't require you to visualize. I mean, when somebody tells me, look, I think space has 10 dimensions, as you're familiar with, right? 11, 22,
I can't visualize it.
Whatever the number.
Yeah,
I
sure.
can't visualize it, but I can really understand what they're saying. I can, it's not obscure what they're saying. So you can get your hands on comprehension or understanding in other ways than visualization. What Bohr was certainly trying to argue was that the reason people found quantum theory hard to understand was that they were asking for a kind of comprehension that was not available. And what we know now is, right or wrong, there are completely comprehensible theories that will give us these numbers, and therefore it's not impossible that there be a comprehensible explanation.
Now, you use the word theories there, and I know that you chose that word with care, because a lot of times physicists, and I sometimes use loose language too, so I'm to blame for some of this as well. But physicists often talk about interpretations of quantum mechanics, when perhaps they should use the word theory, or at least, is that how you would?
Certainly. I mean, you start with, as you say, you start with these observable numbers out of the lab. If you're doing an empirical science, that better be, at some level, what you start with as the thing you're trying to account for. And we certainly know there are different approaches that can account for the numbers we have. Now, those approaches sometimes make even different predictions from each other, but only on the margins and in very difficult situations to realize experimentally. But nobody would say those are just two interpretations of anything, because they straightforwardly conflict with each other, even on the empirics. Nonetheless, often that'll get rolled under, oh, it's just a different interpretation. Sometimes people say, well, if two theories give me the same predictions, empirical predictions, then I'm just going to count them as two interpretations. When you're talking about quantum mechanics, the curious thing is they would never say that when you're talking about, say, space-time theory. So special relativity gives certain predictions, and there's a way that Einstein understood it, and there's a different way that's associated with Lorentz, where he didn't change the space-time structure from classical space-time, but under his understanding, he could still account for all of those same phenomena. And nobody says those are just two different interpretations. They say these are two conflicting theories. They have to be, because they say contradictory things, like, is there a preferred notion of simultaneity? According to Einstein, no. According to Lorentz, yes. So you can't just say, oh, these are just two ways of talking about the same account of the world. They're clearly contradictory accounts of the world.
Absolutely. And where did the word, if you happen to know, interpretation in quantum mechanics first get in? And the reason I ask is, in classical physics, there are, of course, distinct formulations of classical mechanics. You can write down Newton's equations in a straightforward differential form. You can write down a Hamiltonian approach to it. I mean, often we don't call those different interpretations. We call them maybe different formulations of the theory. So what is it about quantum mechanics that brought this word interpretation into the lexicon?
To the historical question, I think that's a great question I don't know the answer to. They're funny words that sneak in, as you may know, with Bell's theorem. The word realism got stuck in somewhere, not by Bell, but later by people who wanted to stick the word realism in so they could think they could get around the theorem by denying realism, whatever that means. I'm not sure when the word interpretation, I mean, we talk about the Copenhagen interpretation, but they talked about the Copenhagen spirit or the Copenhagen school. Those are the actual words that
spirit is a word?
Yeah, spirit is a word that they used.
Meaning?
Meaning, I don't know, a general approach to what science itself is, rather than a specific approach to what quantum mechanics is, I think.
Right.
And it's sort of operationist or sort of empiricist. I mean, it's a little bit hard to nail down. And spirit, of course, gives you a sense this is a very open textured thing. Of course, Bohr, I mean, I'll just say historically, it's pretty clear that one thing Bohr was good at was making allies. So Bohr and Heisenberg and this assistant of Bohr's, Rosenberg, I mean, they were a pretty tightly organized group under the Copenhagen banner. And the opposition, which was Einstein, not small names, Einstein, Schrödinger, de Broglie. De Broglie later said the reason they didn't win the debate was that they all went their own ways. I mean, Einstein disagreed with Bohr, so did Schrödinger, so did de Broglie, but they all disagreed with each other and they didn't form a united front.
And a united front, as we have learned, even from recent historical situations, is pretty important, but we'll put that to the side.
Yes, it is.
Yeah. And so, if we're thinking about Bohr and the Copenhagen spirit or school or whatever, do you consider what is normally described as the Copenhagen approach, is it actually a theory?
No, it's certainly not a theory. What I mean by a theory, I think what anybody ought to mean by a theory, is a presentation of fairly high precision. I don't want to say perfectly precise precision, because we've never had that for reasons we might talk about, but of fairly high precision about saying, here's what I think exists in the world, so what is there? And here's how I think it behaves, so that a dynamics, which is usually presented. Now, in mathematical physics, you use a mathematical formalism to represent what there is, and then in terms of that, you write down dynamical equations, which could be deterministic or not probabilistic, that give you a dynamics. I would say a theory has to have both of those to a reasonably high precision. And if you don't have that, you just don't have a theory. You may have a perfectly good kind of recipe, what I call in my book a recipe for making some predictions, but you don't really have a theory.
Right. So there is an algorithm that a good student could be taught. If you are presented with such and such a problem, here's what you do to make a prediction.
Yes.
And so this involves things like the wave function, which embodies the probabilities of various outcomes, the Born rule, taking the norm squared to get the relative likelihood of one outcome or another. But where in that would you say it fails on your criteria for being a theory?
Good. So in two ways, neither of which I think gets enough attention, because I think there's a general idea that this recipe or this algorithm is somehow almost all-powerful with respect to making predictions. So here are two ways that fails. One is that there's some just plain old laboratory situations to which it does not apply. That is, you can give people this set of recipe, which will work, like if you have a screen and you say, oh, I'm going to say, for whatever reasons, that screen is a position, right, detector, or I have some other device, it's a momentum detector. And once you say that, and then you say, well, if you're measuring, quote, measuring position, use this operator. If you're, quote, measuring momentum, use that operator. Now we're into the math.
Yep.
You give me a wave function, you give me the operators, you give me Born's rule, da-dun-da-dun-da-da, I turn the crank, I get a probabilistic predictions for the outcome of the experiment. But two things, as I say, sometimes I can give you a lab situation to which this recipe just does not apply, because there's no operator. But nonetheless, we can do the experiment and collect the data, okay? So you'd think a good theory of fundamental physics ought to handle any physical situation you can set up in the lab, not just a little subset of them.
You mean like a time operator?
Yes, like for time. I mean, we might, I hope, get into the problem of time, of transit times, and so on. There is no time operator. This is well known, but I'm not sure people have really thought about how significant that is. And the other thing is, in the case I just gave you, I mean, the kind of standard thing you do is you say, oh, this device, whatever it is, it's a position it's a position measuring device, so I know which operator to use, blah, 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 blah. But you'd say, but look, I'm sending some particles at this other physical object. I call it a screen, I call it a position measuring device, but who cares what I call it? It's a bunch of atoms, right? It's got a physical structure. Surely, a proper theory shouldn't care what you call it. It certainly shouldn't care whether you call it a measuring device. A proper theory of fundamental physics ought to be capable of modeling it as a physical object, and the interaction with this incoming particle as a physical interaction, and just derive what will happen or what might happen from that. And that certainly you are not told, and really to this day, no one knows how to do. I only found out within the last month or so, in the literature, there's a thing called the problem of the screen, which is, can physicists actually, in a precise way, physically model what we call screens, where dots show up? And the answer is, no, they cannot. That's a bit of a surprise.
So I'm not precisely sure what that means either, but I mean, I would think I could physically and mathematically model that screen.
Yeah, you would think you could. Give it a shot. I mean, I'll tell you, there are things you think you can do that I know, not from talking to people who've looked deeply into this, and when you think about it a little, like just, I'll give you an example. I mean, I don't want to put you on the spot. Everybody thinks one thing you can cleanly use quantum mechanics to do is predict if I shoot electrons one at a time, as it were, whatever that means, through a screen with two slits, we know an interference pattern will form. You would think the algorithm we have can predict easily the exact structure of that interference pattern. If I collect more and more and more data, I can get to more precision how many particles land where. Nobody knows how to do that with precision. Why?
When you say with precision, is that the key?
Well, what I mean is this. What's going to come? I'll tell you what's going to come to your mind. You're going to say, but wait, I've got the wave function, okay? I know how to propagate it. I know how to get it to the place where the screen is. I know how to square that and use Born's rule. Okay. But notice you can only use Born's rule for the wave function at a certain moment, at a certain time. But those dots, you don't know when that dot is going to form, because the dots form at different times. Now, trying to take account of that. Turns out to be really hard to do. Just mathematically, what do I do? If I try to model the screen, and some people will be able to follow this and some people not. If I try to model the screen as it were making a very rapid succession of what we call position measurements, then you get into what's called the quantum Zeno effect, and your prediction will be no spots will ever form on the screen. That's not right. And if you think off the top of your head you know how to solve that problem, I suggest you could write a paper about it, because nobody, as far as I know, has ever solved that problem.
Interesting. But yes, obviously I would follow exactly the procedure that you summarized, the procedure that we teach our students. But I guess the particular way that you're framing the question, I agree, does give me a little bit of pause.
I'll say just another word for you to think about in your spare time. The normal way we talk about it, a position measurement, is an intervention from the outside at a moment. So we can pick that moment. Like if I were to suddenly flash lasers everywhere and look for a dot to show at that moment. But a screen just sits there. It doesn't have a timer on it. We don't turn it on or turn it off. The time that the spot forms is, as it were, determined by the particle, not by the screen. So the standard way that we do that doesn't apply, because you apply Born's rule at a moment, at a pre-chosen moment.
Sure. Now, Bohr would describe this screen as this macroscopic intervention, and he would say, stop using quantum mechanics at that point, because he drew this line in the sand between the micro world and the macro world. Are there people who still hold to that way of thinking, or is that really just a stepping stone that helped us get to where we are?
I mean, I shouldn't make comments about the sociology of this among physicists, because I haven't done. I can give you a little bit of data about it, but think of what you just said. So first of all, you say, well, let's draw a line between the microscopic and the macroscopic, and this is one in John Bell's paper against measurement. He says lots of words that should never appear in a foundational account. One is microscopic and macroscopic, because where's that line?
Exactly.
Right? It doesn't exist in nature. Furthermore, you think, hey, that screen is just a bunch of microscopic particles following the rules of quantum mechanics. It's not somehow it's not made of a magical classical substance that has different physics to it. So why should I have to make this distinction? As I said, why isn't this just a regular physical interaction between two physical things? Now, the little piece of data I'll just mention is Adam Becker wrote a nice book called What is Real, which was a popular book about Bell and about David Bohm and about Hugh Everett and certain people who were running against this stream of mainstream physics. He was very critical of Bohr in Copenhagen in the book, and he has a degree in cosmology. He's a physicist, a trained physicist. He had a lot of talks about the book in front of physics audiences, and he was expecting very strong objections. And he said he was just shocked that he didn't get it. He would go and give these talks and criticize very strongly Copenhagen, and he'd see nodding heads in the audience. So I don't have myself a lot of data, but I do have the sense that Copenhagen as a kind of dogma doesn't capture a lot of people. Many of them don't have any opinion. They're kind of, I don't know, we never talked about it in my classes, right? I don't really know.
No, it's certainly the case. In fact, here at Columbia, when I've taught the undergraduate quantum mechanics course, pressure is the wrong word, the only encouragement that I've gotten from the other faculty who have taught it over the years, when they see what I want to focus on, because I teach the basics of the subject, but then I do get into issues of the measurement problem, and I do describe Bohmian mechanics and things of that sort. And the only sort of pushback is, don't do that at the expense of time-dependent perturbation theory. Do you know what I'm saying? It's a very, it's really focused on, we want these students to be able to do the calculation, which I completely understand. That's vital to do, but if the student doesn't really understand what the theory and what the holes are, I think that's a pretty big gap too. So totally get it. So when it comes to issues like the measurement problem, can you just give us a quick description of how you see that?
Well, I mean, there are different ways of approaching it, but the simplest one is, the way I think about it is more or less what I said. Again, let me just channel John Bell. I'll do that probably all the time. He said, look, we do things, first of all, physics should be about everything. It's not about what we do, just what we do in the lab, right? It's not about laboratory operations. It's about stars and galaxies and the entire world that exists long before us. And even among laboratory operations, it's very dangerous to call one a measurement, because the word measurement has a connotation. When you say you measure something, you mean before you did this operation, there was some quantity out there, right? When I say, look, I'm going to get on the bathroom scale to measure my weight, I believe I have a weight before I get on the scale. And it's exactly because I have a weight that you can ask questions like, how accurate is this scale after all? I mean, how well is it registering what my weight actually is? And you can do various kinds of tests and compare scales against each other and compare the same scale when I put the same object on it for accuracy. Now, the problem is, I mean, one way to put the problem conceptually is that quantum mechanics is often presented as if measurement was this very important, almost semi-magical moment in physical interactions where something special happens. But then we also tell students things like this. Well, a screen, what does it do? It measures position. Yeah. Right before that dot appeared on the screen, did the particle have a position? No, didn't have one. Right? It just had none.
Right.
But if it didn't have one, then you didn't measure its position. Right? Then that interaction created the position. It didn't measure it. So you're going to end up being extremely confused, quite rightly, by that language. Bell said we should get rid of the word measurement altogether and just talk about experiments, which is, again, just a subclass of all physical interactions.
Right. And the way the algorithm is taught to students, and I suspect that some of those students may be watching this conversation, is it's sort of a two-step process. Step one, use the Schrodinger equation to evolve this wave function that you have some initial data to set the boundary conditions on the differential equation, evolve it forward in time, and then when you do this thing called a measurement, change the procedure, and at that moment, use the Born rule to predict probabilities. And since you know there's one outcome, you imagine this weird notion of collapse of the wave function to the one result that the experimenter found, and you can, using this algorithm, predict the likelihood that that is what they got. So this two-step procedure, step one we understand well. I got this nice differential equation that Schrodinger wrote down in January 1926, but the second part just is the whole, right?
And that shows up even, early when von Neumann writes his book, Mathematical Foundations of Quantum Theory, which was, von Neumann was a mathematician. Yeah. He was sort of looking at the physics and saying, all right, I'm going to clean it all up mathematically. But if you go into that book, in the fundamental axioms, he says, there are these two processes, process one and process two, or process A and process B. And one is, as you say, when no measurement is occurring, then you just evolve the wave function by Schrodinger evolution, which is nice and continuous and deterministic and unitary, and all kinds of math you can learn about how to do that. And then under the other process, you suddenly drastically change it in a non-deterministic way, right? It's no longer deterministic, you only have probabilities. And so you say, well, wait, so the picture you seem to be giving me is that the world evolves by these completely different methods. And when does it do one and when does it do the other? Well, when you measure. Now, if you say that, and you don't have to say that, you can have a theory where it does different things, but you don't tie it to measurement. Yeah. But if you do what they do and you tie it to measurement, then the question, well, when does a measurement occur, takes central stage in physics. And this, Einstein, immediately objected. Or when you make an observation, and Einstein would say, well, who can make an observation? Can a mouse do it? Yeah. Right? Good question. Can an amoeba do it? I mean, these are the kinds of questions Bell also echoed. If you're going to put that dichotomy at the center of your physics, it should be a sharp dichotomy. Yeah. But it isn't one.
Right. And Einstein was also troubled by a particular detail of this unknown thing called the act of measurement, which is if you've got a nice spread out wave function, let's just do a single particle so we can actually picture that wave function just in 3 dimensions. So you have this nice spread out wave function, and then you measure it and you find the particle here, then this algorithm suggests that this wave has changed everywhere, is now spiked, it has its support where the experimenter found the particle. Einstein was like, well, wait, how's that possible, right? You've got this spread out wave in principle through the entire universe, and this act of measurement that you're not really telling me really what that is somehow affecting that wave everywhere. Was that like a central part of his discomfort?
That was the central part of his discomfort. And this also has been buried or intentionally disguised in the history. So Einstein almost immediately in the 20s, I don't know, 26, 27, came up with these kinds of examples where you would have, say, I mean, take a radioactive atom, so uranium-235, and stick it here and then put a spherical detector around it at equal distance. The predictions of quantum theory are, first of all, that there's no preferred directionality, so eventually a spot may form, which we would say loosely is because the atom decayed, anywhere on that sphere with equal likelihood. And at what time? Well, again, kind of at different times. The wave function is sort of leaking out. You can think of it as leaking out from this central atom all the time in a spherical way. And eventually some dot forms. Now, there are two things about that dot. Everybody focuses on one, but Einstein was really focused on the other. One is quantum theory doesn't predict exactly where it will appear, but does give you probabilities. So you'd say, well, I'm giving up determinism. God plays dice with the universe. If that's a complete theory, if quantum theory tells you all there is, then you give up determinism. And people think that really upset Einstein. But the other thing is exactly as you say. Imagine you have this picture and you say, well, this alpha particle or whatever is decaying electron, it isn't anywhere until the spot forms. So a moment before the spot formed here, there was some real physical likelihood, probability, chance that it formed way over here. But as soon as it forms here, that chance immediately has to be annihilated to zero, because you never get two spots. That has to be global and instantaneous change. And Einstein called that spooky action at a distance, or telepathy.
Yeah.
And those are connected with each other. The indeterminism sort of forces the telepathy on you. And there's a nice quote of Einstein's where he says that as the present quantum theory says, that God plays dice and uses telepathic methods, right?
There is such a quote?
Yes, there's such a quote. And the complete quote is that God plays dice and uses telepathic methods, as the present quantum theory says, I cannot believe for a moment. But when I first saw that on the web, the quote was that God plays dice, ... I cannot believe for a moment. I mean, literally.
Well, I've never heard the telepathic part.
And uses telepathic methods got literally cut out because they didn't want to draw your attention. And there's a letter that Bohm writes that makes clear, he says, Einstein really isn't all that upset about indeterminism, right? He could stomach that. But what he couldn't stomach was the instantaneous action at distance.
Right. And it's interesting because, I don't mean to jump around too much, but the famous 1935 paper, Einstein, Podolsky, Rosen, which we'll get into maybe in a couple of minutes, but the reason I bring it up now is, my understanding is that Einstein was somewhat upset at that paper because this issue that he had of this, I guess in this language, telepathic approach to the change of the wave function, it got kind of buried within this more complex arena of entanglement, where my understanding is, he said, we could have explained the issue without having to bring in all this architecture of entangled particles. I could have explained the issue I have simply being a spread out wave function, and now it's not spread out. How did that happen?
I think there are 2 points there. It's certainly true. There's a direct quote where he says after the paper, and again, people think that Podolsky wrote the paper because it seems like someone whose native language was Russian by the use of, and it's clear that Einstein was not completely happy with the paper, and he says that the main point was buried in the formalism, something like that. I think what he saw, and what we can already see from our discussion, was that the paper made a huge advance by dealing not with a single particle, like the example I just gave you, where there's just going to be one dot, but with a pair of particles that could be sent off to labs very far apart. And in order for the argument to go through, he did have to use an entangled state for that pair. It wouldn't work for an unentangled state. So I don't think you can get away from entanglement. There's a kind of weird or unnecessary bit of grandstanding where they try to attack the Heisenberg uncertainty relation in the end of that paper.
Exactly.
You don't need that,
Right.
and that was just a distraction.
Right.
He may have been upset about that.
Yeah, that too. But the point I was making is his fundamental issue of this telepathic collapse, you can do that with a single particle.
Yeah.
You don't need the
Yeah.
formulas of entanglement, but the entanglement does take it further in certain ways,
Right.
Which I'd love to get to pretty much now, because 1935 rolls around and he starts to work with Podolsky and Rosen. The idea of entanglement was already known, right? Schrödinger had already described entanglement.
No.
Are you sure? Because my understanding, again, do correct me if my history is wrong, but I thought Schrödinger earlier had said that he considered entanglement to not be a quality, but the quality of quantum mechanics.
Yeah, but your timing's off. So
that was after 35?
Yeah, the fact, no, so I'll give you the exact thing.
Yeah, please.
1935, the EPR paper comes out. Schrödinger reads it. What we call the cat paper is his response. He says, and there's a footnote where he says, I don't know whether to call this something like a paper or a confession. That paper is his response to EPR. There he introduces the term entanglement. And then in another paper in 1935 that's in the Cambridge Mathematics, he uses this phrase that entanglement is not one, but the characteristic of quantum mechanics that forces a deviation from classical lines of thought. That's in 1935, also after EPR. So I believe both of those papers, the CAT paper and the Cambridge math paper, are written in response to him reading the EPR paper and seeing the point.
Interesting. So why don't you just give us a quick idea of entanglement, just so our audience can be on the same page.
Okay, so there's a kind of mathematical aspect to it and then a physical aspect to it. So let's separate those. As everyone knows, a central piece of the mathematical architecture of quantum theory is a thing we call the wave function. When we learn, all of us learn, to begin, we talk about the wave function of just a single particle. And in a way, that's nice because you can, if we go back to visualizing it, you can kind of visualize it. Because just mathematically, like an electric field or a magnetic field, the wave function for a single particle is represented by a single number associated with every point in space. It's a complex number, so that's a little tricky, but okay, it's a number. You can sort of say, oh, the wave function is there's more of it here than here, right? And compare how much or the squares or whatever. But as soon as you get a pair of particles, a two-particle system or a three-particle system, the wave function no longer even mathematically is a number associated with points in physical space. It's associated with the points in this higher dimensional space we call configuration space. And what happens then with a pair of particles, you can imagine all of the physical states available to just this particle if it was the only particle in existence. Okay, so there's a kind of, a state space of ways it could be. And then for the second particle, a state space for ways it could be. And then there are product states, which means you just say, well, particle A is like this and particle B is like that from that zoo of states. Those are fine. Those are kind of, everybody understands the product states. But just given the mathematics, because we're dealing with a vector space, there are also other states that simply cannot be expressed as this state of A and that state of B.
Right.
You can only try to describe A by mentioning B and only try to describe B by mentioning A. There's a kind of global unification so that the physical state of one can't even be expressed mathematically without reference to the other.
And typically this is set up, just so people can have a picture in mind, typically it's set up where these two particles, they had some interaction, or perhaps they were even born in the same process. If it's like a decay of a calcium atom that's sending photons out back to back, there's something that allows these two particles to have some intimate connection early on, and then they separate, and somehow that separation doesn't make them independent of each other any longer.
Well, that's a little bit of a tricky claim, because I'll just mention, as you know, in quantum field theory, there's a thing called a vacuum state.
That's
It's
true.
a highly entangled state. It is a very, very, very entangled state.
I wasn't trying to say this is the only way, but just to sort of have a picture.
Yes, typically if we want to create in the lab particles that we know to be in entangled states, we do it that way. Right? There's a common source. Say you have two photons that come out of an atom or whatever. Yes, absolutely.
And so you find yourself in this unexpected situation compared to a classical world, right? In the classical world, almost by definition, if things are separated in space, they're independent. Yes, they can influence each other by sending a signal that will propagate across the separation between them, but you can speak about them as independent entities. That's what we mean by reality in a classical world, right?
Yes, and I should just mention, Einstein said almost verbatim what you just said in a nice letter to Bohm.
I see.
He says, if we can, he says, and I was just quoting this letter for a talk I'm going to give. He says, if we consider some conceptual world of physics, and he says, putting aside quantum mechanics, so he says, let's leave quantum physics. We find this, that the idea is that there's a real objective physical world, and that we say that if two systems at the same time are situated in different parts of space, then they each have their own separate reality, right? He says that is what's characteristic of classical physics. It's local in that sense. And he furthermore says, in the field theory, this locality is carried to the extreme. So not only are the physical items like fields, all right, electric field has a state here, it has a different state here. Not only are the objects separate and local like that, but the laws themselves, right? You can ask, are the laws of electromagnetics obtaining in this little region without looking outside, in this little region without looking outside? And he says, this is what's characteristic of physics. And he knew that quantum mechanics was swimming completely against that, right? This entanglement was completely in the other direction, and that's why he didn't like it.
Right. And so what does he do about this? So he writes this paper, and then other people begin to try to make sense in a way that either will give some ammunition to an Einsteinian perspective or not. And what I have in mind here is the whole David Bohm saga. So again, I'm not expert on the history, but I gather Bohm writes a textbook on quantum mechanics, inspired by von Neumann, believes that there is an argument to be made that you can't have definitive quantities in a local theory that will be compatible with the ideas of quantum physics. Shows this to Einstein. Einstein says, no, there's some problem in the von Neumann argument. And this gets David Bohm to think about things.
Okay, so I'll tell you what I know about this. It's a very interesting story. Bohm, as you say, he's an assistant professor at Princeton. He writes a textbook, Quantum Theory, and his intention is to exposit the Copenhagen school more clearly than anybody else has. Because if you try to read Bohr is a very impenetrable writer. He's a very poor writer. And so Bohm's idea was to really clean this up. He actually, one thing he does is he takes the EPR argument that Einstein did with position and momentum, and he reformulates it for spin, which turns out to be very important for what goes forward, although nobody, I think, realized that at the time, but it makes it much easier to comprehend what's going on. So he writes this book, and he's at Princeton, and he very much would like to talk to Einstein about it. I think Gell-Mann tells this story, and he was hoping somebody at Princeton could go bug Einstein. And as he's doing that, he gets a note from Einstein, just spontaneously. And Einstein says, I read your book. I very much liked the book. Would you like to come talk about it? And then, again, I think it was Gell-Mann says, okay, so Bohm goes to the Institute for Advanced Study and talks to Einstein and comes back from that meeting and just says, I'm back to square one. Einstein has convinced me the whole thing is hopeless. This is 1951, he publishes the book. And then by 52, he writes then these papers an interpretation, a quote interpretation. He actually puts interpretation in quotation marks. A quote interpretation of quantum theory in terms of hidden variables. No, I'm sorry. An interpretation of quantum theory in terms of, quote, hidden variables. He puts the quote around hidden.
Right.
And he realizes that you can produce a completely deterministic theory without any measurement process in the fundamental axioms, with just, you've got some particles, they move around. There's also a wave function that guides them in how they move. The wave function evolves by Schrodinger's equation, that's nice and clean and deterministic. The guidance equation, which determines how the particles move, given the wave function, is nice and clean and deterministic. And it makes all the same predictions as standard quantum mechanics.
And so this is a version of quantum, or maybe, I don't know what the right language is, a distinct formulation that allows you to explain the measurement, the data, to get the same predictive power. And yet, in this approach, the particles actually have positions, they actually have velocities, and it differs from classical physics only because there is this new idea of the quantum wave, the wave function, pushing the particles around.
Well, I think it differs from classical physics more profoundly than that suggests. Because the whole idea of pushing is a kind of Newtonian idea.
Yes.
It's the idea of a force. And
Sure.
Newton's theory, the fundamental dynamical equation, F equals ma, the a is the acceleration. The acceleration is the change in the velocity. So for people who know, it's a second order differential equation. And kind of the whole idea of pushing is tied to Newtonian mechanics.
Yes.
The right way, I think, to think about Bohm's theory is that the fundamental equation is not second order. It doesn't involve accelerations.
Just
so it doesn't
it's
involve
V of
forces
T
at all.
equals
Yeah.
H bar of M,
It
grad
directly
psi for
gives
psi.
you
Yeah.
how, given the particles are in this
Yes, I
configuration
agree
now,
with you. Yeah.
and the wave function is such and such, this is how the configuration will change.
Yeah.
So nothing's pushing. I mean, pushing
True.
is
Yeah.
not the right picture to have in
a
your
very
head.
Newtonian description.
Yeah, I
absolutely
mean,
agree.
Bohm used to
Yeah.
talk about choreography, which is
I like
slightly better.
That's very poetic. I like that. But the bottom line is, people thought that couldn't be done, right? That quantum mechanics required that we give up this idea of particles with positions and speeds and just let that go, guys, because that's an old way of thinking about things. And von Neumann seemed to establish that you had to let that go. Some issue with that proof, and then Bohm was able to slip in that crack and actually come up with a formulation. So the interesting, again, I don't want to focus too much on sociology, and I'm glad that we're blending physics in with it, but I do have a sociological question, which is, on the face of it, if someone came to me and I was just learning about these ideas and whatever, the 40s, 50s or something like that, and they said, there's one approach to this theory where you're going to have to give up positions and velocities and move over to probabilities. I'm like, ooh. There's this other formulation where you can still have your positions and velocities. They're a little different from what you would have thought from a Newtonian perspective. You still have probabilities, but at least you've got trajectories. I would say, I'll take that approach, right? Because it seems to require less of a mental rearrangement of the furniture of reality to do that. And yet here David Bohm gives this approach, but it kind of falls completely on deaf ears, right?
Well, so again, now let me give you two more historical data points that are of interest. One is the story of John Bell. Bell is going to school, he's learning quantum theory, he can't understand it. And he asks his professor, but is it really necessary? I mean, with this measurement and these probabilities and so on. And what he reports is that his professor says, yes, von Neumann has proven that no hidden variables theory can return the same prediction.
And just so the audience knows, hidden variables here would be the usual non-hidden qualities of position and velocity.
Here it just means that you actually have particles that are moving, right? Particles that actually have positions. If the spot forms here, it's because a moment before that spot formed, the particle
right
was
near
really
there.
near there, and
Yeah.
it was heading in that direction.
Yeah.
So Bell reports that his professor tells him von Neumann has proven this can't be done. And Bell says, I didn't know any German, and von Neumann's book had not been translated. So I took it for granted. I just figured my professor tells me a famous mathematician has proven X is impossible. I guess X is impossible. I should stop, beating myself up over it. And then he says, and then one day I woke up in 1952 and read Bohm's paper and said, but wait, Bohm just did what you told me von Neumann proved can't be done. So Bell could understand what Bohm did and see that it all worked, right?
Yeah.
And by that time, von Neumann's book had been translated. And then he can read the book, and later in an interview, Bell says that there's not a mathematical mistake in the book, of course. I mean, von Neumann was a great mathematician, but there, of course, for any theorem, there are assumptions.
Yeah.
And he says, one assumption, he says, is foolish. He says, you can quote me on this, it was just a foolish one. Now, the other interesting data point is that very soon after von Neumann's book, it wasn't that Bell was the first to realize this. Greta Hermann, who was a philosopher, and a woman, which were two strikes against her as far as any physicist was concerned, also understood this error, this undefensible assumption and pointed it out. And there's another data point, which is that someone was talking to Einstein, I believe in the 50s in Princeton, and Einstein said, well, I'm working on a deterministic theory that will give me all these predictions. And they said, but what about von Neumann? And they report that he went to his shelf, pulled von Neumann's book off, opened it up. We have no reason to believe this. And he pointed, and we know what he was pointing at.
Right.
So the flaws in what von Neumann did were actually quite well appreciated by people who cared enough to think hard about it.
Right.
But you get the sense that many physicists were perfectly happy to have von Neumann's word that they don't have to think about it. Right?
Just made it cleaner and simpler and easier.
Well,
right.
I can stop worrying about, do we really know it's indeterministic and so on, because von Neumann, the great mathematician, has proven it must be so, and that lets you off the hook.
Right. Now, another thing that is a real issue or quality or should be brought to light in our conversation, that's of course well known in circles of people who think about Bohm's approach, the way in which this wave function, I won't use pushes, choreographs, that was the word, the way in which it choreographs the motions of the particles has within it this non-local aspect, which is you can fiddle with some particles over here and it affects the motion of the particle way over there.
Yes.
And so oftentimes, even today, people will say, oh, but you've got this non-locality, which is the technical way of describing this. I think the right answer to that is, but quantum mechanics itself has non-localities. It's just sort of hidden in entanglement, the thing that we discussed earlier. Is that your response? I mean,
look, so the exact, and it's really how, of course, Einstein knew about Bohm's theory. It's really the same as de Broglie's theory, which was already in the 20s, well known. So Einstein knew about that theory. And he knew it was a deterministic theory. And this again goes back to if what Einstein was so worried about was indeterminism and God plays dice, why didn't he just get on the de Broglie bandwagon or the Bohm bandwagon?
Yeah.
And the answer is, as you say, in that theory, the non-locality, the spooky action at a distance, is in your face, right? Because it's a theory. So when you have a theory and it says exactly what there is and how it behaves, you can start asking very clear questions. Well, what would happen in this experiment if this piece of apparatus had been that way rather than this way, right? The theory will tell you.
Yeah.
And what you can see is that in certain circumstances, if we separate Alice and Bob into their labs far apart, and that's again in the EPR case, we have these two particles so we can send them off in very distant locations. It's just manifest in that theory that sometimes what Bob sees in his lab will depend on what Alice does in her lab. This was the spooky action at distance. This was the telepathy that Einstein didn't want. So he knew about the theory but rejected it. He wanted a local theory.
Yeah.
And I don't blame him, right? I don't think that Einstein can be criticized. He really thought the progress of physics through electromagnetic theory, special relativity, general relativity, all those are local theories in his sense. He thought the progress of physics was telling you the world is local. And he rejected a theory that didn't have that feature. Now, what interested Bell, and now this is after, unfortunately, Einstein died, he says, well, I know I can get determinism because Bohm has shown me how to do it. Can I also get back locality and still keep all the predictions of quantum mechanics? And that was the question that Bell hit on. It wasn't his day job to think about this.
Yeah, he was just working this on as a hobby kind of thing, right?
He was doing it on the weekends. Eventually, he got a sabbatical and sat down to go through all the so-called no hidden variables proofs and wrote a paper about them and their weaknesses. But then he hit on Bell's theorem and what the theorem shows.
And this is like the early 60s?
This is 63.
Yeah.
What the theorem shows is that no local theory of the kind Einstein wanted can possibly reproduce the predictions of standard quantum mechanics. So the non-locality can't be gotten rid of and keep the same predictions. And then when you go into the lab and see the predictions are correct, you say, well, forget about quantum theory. The predictions are correct. Bell has shown us that these kinds of phenomena can't be explained in any local way.
And when you say forget about quantum mechanics, it's kind of important. You're saying regardless of what the explanatory fundamental structure is, the results in the laboratory cannot be explained by any theory that is local.
Local in the sense Einstein wanted it to be, relativistically local.
Right.
It's very important to understand that Bell's theorem is not about quantum mechanics at all.
Yeah.
It's like, okay, I have a lab, Alice can do this or that, Bob can do this or that. They're just going to record some data. Here's some correlations between the data that Alice record and the data that Bob record. That cannot be produced by any local theory.
Period.
And
the amazing thing is, just going back to how we began, there are versions of exposition of Bell's theorem that a seventh grader could understand, right?
Yeah.
You don't really, you can basically set it up where, if you get this over here and this over here and trying to assume there's locality, you simply can't explain the data, period. And you can just do this counting on your fingers. So it's a very straightforward argument, very straightforward proof. It's revolutionary. And again, just going back to how we began, somehow it doesn't immediately turn the world upside down.
Yeah, it's interesting. It hit some people. It hit me when I read Despaignat's Scientific American article about it, even though that article is kind of a little bit confusing and not right. But he gave enough of what was going on that if you thought about it, you'd say, wait a minute, this is really, really, really strange. It hit some people who were kind of on the fringes of physics and a little bit hippie, trippy.
I think that may be part of why it didn't spread as wide, because it's sort of, at least, again, I could be rewriting my own past, but I think I had the feeling that this whole Bell EPR stuff, it was just like the new age physics people that cared or were thinking about it, and somehow for a hard-nosed physicist who was going to actually be doing real calculations, that just wasn't something to think about.
Well, the interesting thing is that idea of exactly what you said, a hard-nosed physicist doing calculations.
Right.
Because there's another piece of rhetoric that goes along with this. Everybody cites Feynman before Bell in his famous lectures and elsewhere, and he says, nobody understands quantum mechanics. I don't understand it. I've never gotten used to it. I've never felt comfortable with it. Maybe I'm just too old. Feynman is saying this.
Yeah.
And that's, again, propagating this idea that don't think you're going to be able to understand it, right? The understanding isn't really available, something available here. But later in the 70s, Feynman writes a paper where to tell you the truth, what he did was rediscover on his own Bell's theorem.
Oh, really?
About a decade after Bell.
I see.
And makes a big deal out of it. He says, all my life I've thought there was something weird about quantum mechanics, but now I can actually reduce it to an equation, that this must be larger than that, right? And it's really just Bell's theorem. I think he either never read Bell or certainly didn't appreciate it, but somehow when he came across the same proof on his own, all of a sudden it struck him as, oh, this is what's so weird about quantum mechanics.
Yeah, I can imagine that. So the other quality, though, of the Bohm approach, which again is not one that is maybe we should say it's not widely taught among physicists. Sure. Part of it is this red herring of saying, well, the non-locality is in your face, but if there's non-locality, whether it's in your face or not,
it's not a bug, it's a feature. Is what I always say,
yes,
right?
Exactly.
You know, Bell showed us it's a feature.
Right.
Einstein thought it was a bug because he didn't know about Bell.
Exactly.
Good for him. Once you have Bell, you say, no, it's a feature.
But the other thing which is not a feature is that it is challenging to make a relativistic version of this approach. So non-relativistic quantum mechanics that an undergraduate will take and say their first year, their first exposure to quantum mechanics, typically we just do the non-relativistic Schrodinger equation. It allows you to do things like hydrogen and particle in a box and things like that. But then if a student goes on in physics and if you're actually going to be in the field, you have to include relativity, and typically we do that by getting to a quantum field theory, a relativistic quantum field. There are non-relativistic quantum field theories too, but that's the framework. So where do we stand in this Bohmian approach, being able to take that next step?
Yeah, so there are things to say on both sides of this. Let me say on each side of them. I don't know of any way to implement the basic idea of a pilot wave theory, and there are different versions and you can do them for fields and so on. I don't know of any way to implement that without using what we in the business call a preferred foliation of space-time, which is the idea that you have space-time, it's four-dimensional, but it is by nature sliced up, which is a foliation called a foliation, sliced up into a series of, as it were, leaves that have a definite order. And
the leaves are all of space at a given moment of time.
Right, so it's what, it corresponds to what Newton called absolute simultaneity. So, and that's of course the way we think about the world until we get to relativity. You say, I snap my fingers, okay, that was an event, and there is, as it were, a snapshot of the entire universe, what was going on right then, right? What was going on here and in LA and on the moon and on Alpha Centauri. Now, we won't know what's going on Alpha Centauri for quite a while because we've got to get the news, but still something was going on there, right? That was Newton's picture of his, he says an instant of time is spread out throughout the entire universe. That's the normal picture. That is what we now call a preferred foliation of space-time. Relativity got rid of that because Einstein realized he didn't need it for his purposes. And his purposes were basically getting Maxwellian electrodynamics and then eventually a theory of gravity that was pretty much like Newton's, not quite the same predictions, but close enough to explain the success of Newton, that he could do all that without a preferred foliation, without absolute simultaneity. And I think that's why Einstein was so upset about spooky action at a distance, because it requires, if you say doing something here has an effect way over there, well, just pairing up the cause and the effect gives you a preferred foliation.
Yeah.
So I don't know of any way to implement something like the pilot wave approach without a preferred foliation. Now, some people like to say, well, okay, but I can give you a rule where for most wave functions, not all, but for most wave functions, you just give me the wave function, and from that I'll give you a foliation. I'll kind of derive the foliation from, as it were, the state of matter. Mm-hmm. And that rule can be relativistically invariant, right? They say this is a more relativistic. My own view is, put the foliation back in. Looks like we need it. What Bell proved, I think what Bell proved is that there's non-locality, and the easiest way to implement non-locality in a theory is to postulate there is a preferred foliation and to use it in writing down your equations. That's
But there's two things. So you can have a preferred, you have to know exactly what that means, but you can choose a foliation. Usually we say, yeah, sure, you can choose any foliation you want, but we want there to be some relativistic invariance of the formulation. And so if you do choose a foliation and realize Bohmian mechanics in that framework, and I don't know the detailed literature on this at all, can you do it in a way that does respect a change of foliation that comes? Okay.
That's the point. And you should know this because in David's book, David's first book, Quantum Mechanics, David Albert, Quantum Mechanics and Experience, he gives you a very nice example coming from EPR and coming from Bell. Alice is over here, Bob is over here. We send them an entangled pair of particles. They're going to do some spin measurements on them. And in Bohmian mechanics, you do this with a foliation. You're going to get either a result, say, of Alice's shows up and Bob's shows down, or the other way around. So everybody agrees the quantum mechanical predictions are, it'll either be this or this, maybe 50% chance of this, 50% chance of that. David gives you examples where in this theory, because it's a precise theory, you use a foliation, and whether you get this result or this result will depend on whether Alice does what she does before or after Bob does what he does,
which is a frame
relative to that foliation.
Got it.
So if you suddenly switch the foliation, you'd actually get a different prediction.
I see.
For that individual case, right? The statistics would be the same for many repetitions, but for that individual experiment, the foliation plays a role in determining whether it's this outcome or that outcome.
Right. And you're saying that doesn't necessarily trouble you when you see that. You're like, hey, maybe that's...
Well,
because for most of us, that's very troubling.
Well, it's and certainly this is a standard reaction from physicists. As soon as you say, I'm using a preferred foliation, I'll just tell you a little story. I ran into Scott Aronson, you probably know Scott, and I said I was working on a certain kind of theory, blah, blah, blah. And he says, oh, but aren't you going to get into trouble with these causal loops? And I said, no, I'm using a preferred foliation. And his total response was, that was it. That was it. It's like, all right, I'm working on a theory that'll solve all these problems that I can write down and blah, 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 blah. But gee, I don't like it because you've got a preferred foliation. Right. Now, I think now you have to stop and think, where did this come from? And the answer is clear. It came from relativity.
Of course. It's
because
so
there's
beautiful.
no preferred foliation in relativity. Yeah. But again, special relativity was designed for Maxwellian electrodynamics, which doesn't need a preferred foliation. Right. General relativity showed you how to do gravity without a preferred foliation that's close to Newtonian gravity. That's what Einstein was trying to do.
Sure.
They didn't know about quantum mechanics. They didn't know about Bell's theorem. I mean, I like to think that Einstein, if he had read Bell, would have seen the point and would have said, maybe I shouldn't be demanding.
So you don't think it would have been the Scott Aronson?
I don't know. I don't think, I mean, he was Scott Aronson when he was just thinking up theories and says, oh, here's a theory, it has a preferred foliation, I don't like it. Right. But once you have Bell in front of you, of course, what Einstein didn't like was the spooky action at a distance, the non-locality. Once you realize there is non-locality, it's kind of a very simple, the easiest way, as I say, the easiest way to implement it is to have a preferred foliation.
And is there, what's the prescription for choosing that preferred foliation?
I'm not sure what you mean by choosing. I mean, for example, I'm just playing around with a theory that has one built into the space-time structure. It's just there. So I don't know what you mean by choosing.
So from the get-go, you say
nature chooses
right.
it.
You're saying from the get-go, I'm just
part of the way standard relativity has a light cone structure, right? It has one. You say, but how did it get chosen? It's just part of the theory is that that's part of space-time, right? It's part of the space-time structure.
Right.
Why do I believe in that? Because I seem to need it to do physics. I believe in the structures that seem to be, if not forced on me, very heavily, right, suggested to me by the physical phenomena. And violations of Bell's inequality, which are the physical phenomena, really, to me, are a very good motivation for thinking, let's open up our minds.
Right, right. Interesting. So Bohm is one interesting direction as we spend some time on. Many in our audience and people more generally have heard of the many worlds approach as sort of a another direction in which people took these ideas. Maybe take us through a little bit of that, and we can then talk a little bit about where things stand on that way of thinking about things.
Yeah. So my preferred way to triage approaches to quantum mechanics, what again people will call interpretations, but I'll just say are different families of theories, is to start with the fact that there is just a flat contradiction between three different propositions, all of which one would like to hold, right? Intuitively, you come into the game and you'd say, these all seem quite reasonable to me. Or anyway, my life would be easier as a physicist if I could hold these. One is, we know that quantum theory is using a wave function. Question, this is a question EPR asks, is it complete? Which just means, if you tell me the wave function for a system, does that contain all the information about the physical state of that system or not, right? If it contains all of it somehow, then it's complete. Then two systems ascribe the same wave function are physically identical in all respects. You'd kind of like that because, you know, you've got wave functions and you've got Schrodinger's equation and you kind of know how to play with them, and so it would be pretty straightforward.
Yeah.
The second thing that once you've got the wave function, you then ask, well, how does it evolve in time? You'd like it always to be Schrodinger evolution because it's this nice, clean, deterministic, unitary, simple, basically pretty simple evolution mathematically. Does it always do that or not? As we said, if you look at von Neumann, he says no, it does sometimes, but other times it does this other thing, it collapses. Very different process.
Yep.
And that duality of process is very worrisome, and you wonder why does it do it sometimes and other times. And there are collapse theories that tie the collapses to measurements. Those are especially worrisome because we don't know what a measurement is. There are other collapse theories that don't tie it to measurement, that just have it collapse randomly from time to time at a certain rate, the so-called GRW theory. That's a little better, but it still has this duality of smooth collapse that seems a little hard. So you ask, is the wave function complete? Does it always evolve by Schrodinger evolution? You'd like it to be complete. You'd like it to evolve by Schrodinger evolution. And there's a third thing you'd sort of like, which is that if you do an experiment like the famous Schrodinger cat experiment, you'd like to say, I started with one cat, don't I end up with one cat? One cat in, one cat out, right. And the cat coming out is either alive or dead. Right. I mean, Schrodinger thought, that's something we know about the world. We know if we take a single cat and put it in a box with some, you know, a mechanism and some cyanide, that at the end of the day, that very cat is still one cat, and it's either a live cat or a dead cat. That seems like something you'd like to maintain. Yeah. Now, it turns out you can't maintain all three, right? Those three, you can't, if you insist the wave function is complete, and you insist that it always evolves by Schrodinger evolution, you can't maintain that the cat ends up either alive or dead. So you have to give up at least one of those three hypotheses. The pilot wave theory gives up the completeness of the wave function. The collapse theory gives up the Schrodinger evolution. And the many worlds is what you're stuck with if you refuse to give up either of those two. And you say, okay, I guess I have to say I started with one cat and I ended with, well, people often say two cats, a live cat and a dead cat, but that's not right. For Schrodinger's case, there are an infinite number of dead cats because how the cat died, I mean, Schrodinger's got ways. You know, it depends on when the thing decays and the cat would die. So, you know, and then you, okay, now you're already in a mess because you say the world sort of doesn't seem like that. And then you have to go through all of these hoops to try and, first of all, make any sense of the theory, and then especially to make sense of probabilities, because you say...
But just take it a little bit further, I mean, just to bring your description to the picture that I think people have heard before. So if you are going to go in the many worlds approach, you're basically coming to a picture where you, the measurer of the state of the cat, will encounter that cat alive in one universe, dead in another, dead in another, and so on and so forth. And so the many worlds are the many possible outcomes allowed by the spectrum of possibilities that are embedded in the quantum wave function.
Yeah, although again, I mean, one advantage the many worlds people can claim is they don't have to mention measurement. So you said you the measurer,
Yes.
right? The theory says, Schrodinger says, look, go into the lab and set up this situation, and we could do it. I mean, we could. It's cruel. We couldn't to kill the cat, but you get the idea. There's nothing hard experimentally about the situation.
Yeah.
Quite apart from anybody else, the many world says, well, after say 10 minutes, if we could see all of physical reality, there would, as it were, be a branch where the cat is alive and a whole bunch of other branches maybe where the cat is dead in different ways. That's independent of us looking at it.
Right.
And then you say, but what if we go look at it? You've now got all these, as it were, different cats.
Yeah.
Then they say, then what's going to happen is that we start with one cat, we now have many cats, we start with one you, we're now going to have many yous. There'll be a you that's, as it were, inhabiting the branch with the dead cat, and you're grieving, and another you that's inhabiting the branch with the live cat, and you're playing with the cat, and you're going to fission in this way just as the cat did.
Right.
So the term measurement does not appear in the foundational principles of many worlds. So it does have that conceptual advantage.
So in that sense, it solves the measurement problem by
avoiding
it.
Yeah. I mean, the best way, you shouldn't, the only decent way to avoid it is by formulating a theory that doesn't mention measurement.
Right.
So it never comes up. That's what Bell demanded. That was why measurement was on one on this list of forbidden words that he had, which included macroscopic, reversible, irreversible information he didn't like. There were lots of words he said, these aren't sharp enough physically to be appropriate terms to be using in a fundamental physical theory.
Right. And just to, again, I love the organization that you were describing, just to sort of spell it out. So this approach, I guess, is Hugh Everett, 1957, is a person who was a student of John Wheeler. So he's assuming that the wave function is a complete description.
Yes.
So very straightforward. He is assuming that the Schrodinger equation that we teach our undergraduates is the equation, be all and end all of the entire theory. And that's where those two assumptions take him, to this reality in which there are what we would normally describe as world upon world upon world upon world.
I mean, I should say a word historically about this. If you read Wheeler's original paper, he called it the relative state interpretation.
Largely, as I understood it, because he wanted Bohr to not immediately reject it.
Well, whether that was the reason or not, it's certainly when he talks about the relative state, that's language that has dropped out of the modern version. The modern version runs through something called decoherence, or attempts to run through something called decoherence in a way that, as I understand it, Wheeler's original approach didn't. So it's a bit hard to get your hands on exactly what Wheeler was proposing in 1957. He says, what he says is, look, suppose I have an entangled state of this pair of particles. Okay, so kind of neither one has its own state, as we were talking about. I can't describe this one independently. But he says, okay, but if I, as it were, just out of thin air, postulate some state for this one, I can now plug that arbitrary state in here and now calculate a relative state of this one. So this is the state of this one relative to what? Well, not relative to the actual state of this one, because this one doesn't have an actual state, but relative to this, arbitrarily chosen state. So it's a little hard to understand what he's proposing there. The people think that that problem can be solved by decoherence, and that's a complicated question.
Right, which maybe we'll have time to, but I want to get to the more concrete issue that people have certainly banged their heads against the wall for a long time on, which is a simple statement that quantum mechanics, as we understand it, is a theory that speaks of probabilities of one outcome or another.
Right.
In this many worlds, this Everettian approach, we're basically saying that every possible outcome happens. So if you, for instance, want to say that some outcome is extremely unlikely, what does that mean in a theory where you're guaranteed for it to happen in one of these worlds?
Yes.
And so where do you...
I think I think that's exactly right, and that's conceptually incoherent. And you can put it in very concrete terms, right? I mean, suppose I literally have my pet cat, and I'm being forced by some nefarious agent to put my cat in one of these Schrodinger-like boxes But I have a choice between two boxes. And in quantum mechanics, normal quantum mechanics would tell me, if I do this apparatus, there's a 90% chance the cat lives and a 10% chance the cat dies. And if I do that one, it's the other way around, okay? 90% chance that it dies and 10% chance that it lives. I, loving my cat, would clearly choose, right, the one that gives the higher chance of survival. I, of course, would then cross my fingers when the actual experiment goes, because, you know, the breaks could be bad and so on. Now, from the many worlds perspective, they're going to say, look, no matter which choice you make, there'll be some worlds where the cat lives and some worlds where the cat dies, and some worlds where your continuing consciousness is with a live cat and some worlds in which it's a dead cat. And the only difference is on this side, the live cat part has high amplitude, and on this side, the live cat part has low amplitude. And then you say, yeah, but can I tell the amplitude of the world I'm living in? Does this amplitude you're talking about have any empirical marks or anything? And you say, no, it feels just the same to be in a high amplitude as a low amplitude world. And I'd say, but then what's the difference? Now, if they say, but your cat is much more likely to live, no, they can't say that, because in both cases, you get some live cats and some, and you can't really count the cats and all these things. I mean, so I just don't think you can make sense of probability in a situation.
So I'm sympathetic to all that, but I'm also aware of some really smart people who for a very long time have worked on this, to the point where I remember, and this is now going back a number of years, so it's not even that recent, I was engaging one of them in a conversation of this sort, and their reaction was not Scott Aronson's reaction, but it was, oh, come on, we've already solved that. Just leave me alone, it's already done. We understand the probabilities, and let's just move on. It all works. And so and this is sort of coming mostly from the Oxford School, like, you know, these are wonderful people. This is not meant in any way, you know. So where's the disconnect? Where you have people who feel that they've resolved this issue?
It would be curious. I'm not sure what to say, because even the people in the Oxford School who are the most serious about it, like David Wallace, I mean, David tried to come up with a very complicated decision theoretic justification for treating these squared amplitudes. So what you really have, according to the theory, is the wave function, and it has amplitudes. That's okay, that's part of the physics. And then you take those amplitudes and square them. You have to square them because they're complex numbers. And then you, as it were, act as if the squared amplitudes were probabilities in the normal sense of probabilities. Now, there are some very complicated attempts to give decision theoretic arguments for why you must, or it's a reasonable thing to act that way. When you look in precise detail, because you can look, because they're trying to prove theorems, what are the assumptions that go into this theorem? You find, first of all, a whole lot of them, more than you would have expected. Second of all, a lot of them have to do with decision theory, which you wouldn't have expected to show up when you're doing physics. And third of all, some of them are just weird. I mean, it wouldn't naturally occur to you that this is an assumption to make. I think this all has more the feel, as we say, of rationalization than reasoning, right? Reasoning is a process where you take some a priori or apparently plausible premises and figure out what follows from them and follow the argument. And rationalization is where you know the conclusion you want to get to and you find an argument that will lead you there. And some of these people, they want to be many worldsers no matter what. And so if you raise an objection, they're going to find some way out, some wiggle way out of it. I don't think anybody finds any of those attempts terribly convincing.
And you would not, again, you would not put a preferred frame of foliation into the latter category of, you do consider that to just follow from the very natural...
Newton believed in it.
Right.
I mean,
Newton believed in a lot of things.
But it was a big deal when we got rid of it. It's not like, it's not like it's this out of nowhere thing. Right. It's actually what you originally believed in, right?
Right, but Newton also believed in alchemy and God and all sorts of things.
But I mean, it's central to his actual physics, not his side.
No, but I mean, he
his
also
side hobbies that we don't
obviously
really
he
care
believed
about.
in qualities of the world that we certainly
Sure.
don't. I mean, arbitrarily high velocities. He believed.
It was a monumental achievement of Einstein to point out that one could get away without a preferred foliation.
Yes.
Although you pay a price, you have to have light cones, you have to have other space-time structures that Newton doesn't have,
Yeah.
right? It's not as if it's just cleanly simpler than Newton. You take out the preferred foliation, you put in a conformal structure and so on. You know all about
course.
that. It was a monumental discovery of Einstein that was possible. But I will say one more time, Einstein did not have on the plate in front of him, by the way, can you explain violations of Bell's inequality?
Right.
And it turns out to be really hard to do without it.
Yeah. So where do you think that we stand right now? If you were to list the top 2 or 3 remaining mysteries of quantum mechanics, I mean, do you have ones that immediately strike you as the critical things that we've got to still figure out?
Well, we have these different, very large-scale, different umbrella approaches. We have the pilot wave approach, which the standard example is Bohmian mechanics we talked about, but there are other ways you can implement that basic idea. You have objective reduction or objective collapse approaches, which have been implemented in different ways, some of them continuous, some of them discontinuous. Then you have the many worlds. I mean, I think those are the three big things. So one thing you would really like to know is, can we at least knock out one of these 3 or 2 of the, ideally 2 of these 3 and at least focus our attention.
Right.
Now, the collapse theories always, in principle, make slightly different predictions than the non-collapse theories, but it's very tricky to test for those. It's looking, as time has gone on, the parameter space for those theories that it still fit with what's observed is getting smaller and smaller.
And the parameters are like how often these collapse processes
how often
happen
the collapses
and
occur and how narrow the wave function is after the collapse.
Right.
So there's and it may be that in 10 years experimentally it'll be wiped out. It's possible. Because both many worlds and the pilot wave theory are non-collapse theories, you don't have that kind of argument that even in principle, if you can make sense of the many worlds, making any predictions, I mean, it's this kind of thing. It's not quite clear how you make any predictions with it. If you could, you might say, I don't see how they could differ. Although I personally think if there's a preferred foliation, and I think it's a plausible thing to pursue. Then the next question is, well, can I tell in the lab what it is? Can I do an experiment that would reveal it to me? Now, you're not guaranteed you can, but you're not guaranteed you can't. The only way to answer that question is to have a precisely articulated theory and analyze it. Now, what I have found out very recently for me, and to me is very exciting, is that one thing one might expect or imagine you could do is send superluminal signals. If you can send superluminal signals, relativity's gone, right? Everybody's just gonna have to say, sorry, Albert, it was a nice idea, didn't work out.
So just hold that for the audience. In the usual approach, where there's non-local interactions, we stress that there isn't an actual message that superluminal influence is able to communicate. If you got spins up over here and spins up and down over here, the results will be a random collection. If it was 50-50, random collection here. And only when you bring them together and compare do you find, oh my God, up, down, up. Is there information in the data? So that's a slower than light process, even though there seems to be some faster than light connection of some particular sort. But you're not talking about that. You're talking about an actual superluminal signal. Using this actually send a message.
Right. So the 2 steps are, I would say, 3 steps. Einstein thinks ain't nothing goes faster than light. Not causation, there are no non-locality.
Right.
I don't want any of that. Bell says, sorry, here's some data. You can't explain it under the assumption there's no superluminal causation. So we're stuck with that. Now, from my point of view, just without any argument, I would say, gee, if there's superluminal causation, why can't we, if we're really clever, why can't we use it to actually send signals for our use? Remember what that means. It means on one side, we call the transmitter, there's something that we can freely set, right? So Alice can set her apparatus this way or that way. And on the other side, we call the receiver, there's something Bob can see, can actually observe. And the idea is that if there's a correlation between how she sets and what he sees, then they can signal. Then by setting it this way or that way, Bob can make an observation and say, either for sure or at least with better odds, this is probably what Alice did. If there's superluminal causation, and I think Bell shows there must be, an immediate question that you ask is, well, why can't I use it to signal, right? I mean, I kind of expect you could. Now, there's no guarantee. Maybe nature is put together in a very specific way so that even though there has to be non-locality, it can't be used for signaling.
I've always assumed that that is the case, that somehow relativity, properly circumscribed, survives by the skin of its teeth, because even though there's this kind of superluminal connection or instantaneous connection, you can't tell someone to sell stock.
Right.
You know.
So I will report to you that Will Cavendish, who actually was a student here at Columbia and is a mathematician, has been looking at various proposals, specific proposals, and finds in the literature, in the standard physics literature, that for almost all of them, you can superluminally signal. The people haven't realized it, but they write down some equations and they say, do it this way, this way. If you know
in which context? Is this like a Bohmian? Or
no, he's not a Bohmian.
So
it's true. It's true you can do it in certain ways of implementing Bohmian mechanics, but he is not a Bohmian. He's looking at all kinds of standard field theoretic. I mean, let me put this very specifically in a way you'll understand, maybe some people in the audience will understand. It's often said that relativistic quantum field theory is relativistic because it is built into it that you can't send signals. This is why this isn't, you have to say, well, what is it to send a signal? It's that Alice does something or other, could be anything, and there's a correlation between what she does and the statistics of what Bob sees. He could be looking at anything. The technical formal condition in quantum field theory is something called the equal time commutation relations. What they tell you is that if Alice does something we call making a measurement, and Bob does something we call making a different kind of measurement, then the statistics of what Bob sees can't depend on what Alice does. But there are lots of things Alice could do that we would never call making a measurement. And there are furthermore things Bob could look for that we don't know how to represent as the outcome of a measurement, like arrival times. We talked about that at the beginning. We just don't know. We can't fit that into this paradigm. So even there, when people are being very careful about quantum field theory, not from a Bohmian perspective, but they have proposals about, for example, how to make predictions about arrival times. Proposals, we talked about the screen problems, proposals about how to deal with screens. If you look at those very carefully, they allow for superluminal signaling.
So this is new to me.
It was new to me too.
So if I understand correctly, and again, steer me if I misunderstood what you said, normally I would think in relativistic quantum field theory, I've got these operators at space-like separation, they commute, period, sort of, end of story. But you're telling me that that's a limited way of thinking about the things that an observer in the laboratory can actually do.
There are things I can observe in the lab that don't correspond to any operators. I mean, this is, again, a standard example that people just don't think about enough, are arrival time. So here's an experimental setup. I take an electron or a single particle, I put it in a trap. It has to be a certain kind of trap, a pole trap, it doesn't matter. I put it in a trap, I kind of hold it here and prepare it in some quantum state that we all agree that's what it is, a spin state. And I have a waveguide that runs this way to a screen. And at some predefined moment by a clock, I drop one wall of this and I'll let the wave function, as it were, go down this waveguide. And then at this screen, eventually a dot will form, and I not only record where, but exactly when, with as much temporal precision as I can get. right? Femtosecond clocks. Right, that gives me some data. What is the time lag between dropping this and dots forming? Now, every time you do the experiment, you'll get a different result. The dot will form both in different places on the screen and at different times. So you get a nice histogram of all of this data. Nobody knows how to predict that because there's no time operator, right? Nobody really knows the spatial distribution for reasons we talked about, but it's clear with time, there is no time operator. And there are situations where if now, instead of doing that, I have an entangled pair, and I send one this way to Bob, and I send one this way to Alice, where at least you can imagine Alice doing something that will affect the arrival time distribution of Bob's particles. So that if she does one thing, you get one distribution. If she does something else, you get a different distribution. Then she could signal Bob, right? I mean, it might require a lot of copies or you're doing them all at the same time, but Bob, on the basis of what he sees, could make a better than random guess about what Alice did. So that would be Shannon information being sent.
I see, interesting. So let's just finish up with one other area, if you have a few more minutes, which is this. We've been the whole time speaking about these ideas which we embody in mathematical equations. Schrödinger equation, Born rule, Newton's equations, Einstein's, all these things that have come up in our conversation. How do you think about those equations in the following sense? When I was younger, I used to think about those equations as, I think I was naive. They were reality to me. Like, there it is. This is how the world works. Now, obviously, sometimes equations change, so you have to ask yourself, what do you mean it's reality if it changes? But I wasn't really, I was just like, we're going to find the equation. Yeah. As I've gotten older, my view has really shifted radically to a place where this is our best model of the external world. We come up with these mathematical concepts in order that we can get ever more precise descriptions of things, but it's all just human-made descriptions. So that's kind of both ends of the spectrum, and I've kind of gone from one to the other. Where do you sit in there?
I'm not quite on your spectrum here, so let me make a distinction. Mathematical physics, by definition, is a discipline that uses mathematical structures in an attempt to represent the physical world. Okay? And that's a representation relation, which is something philosophers think about a lot. How does language manage to represent the world? Yeah. In this case, the language happens to be mathematics. Then make a further subdivision in mathematics. There's number theory and algebra that involves numbers, and there's geometry, which doesn't involve numbers. This is a distinction the Greeks made. They really took mathematics and said there's geometry, there's arithmetic, these are different subjects. It was in arithmetic, you eventually got algebra, which was a very powerful tool for solving algebraic equations, and then there was a whole thing of trying to take physics, which had been stated in the language of geometry, right? Newton, if you open Newton's Principia, you will not see an equation. You will see a whole bunch of very complicated Euclidean diagrams, right? He wasn't using numbers, he was using geometry. Yep. Descartes figured out how to use coordinates to translate geometrical problems into numerical ones, solve them using algebra, and translate the result backwards. Now, I think it should immediately be a puzzle. How did numbers get into this at all? Because the world isn't made of numbers, right? I mean, supposedly Pythagoras thought a horse was the number 10, but I have no idea what he was talking about. But our intuitive idea is, but the physical world is geometrical. I mean, look, here's a round, more or less round object, right? You can see how Euclidean geometry could kind of apply to that pretty well. So the first thing to ask is, well, what is the math I'm using anyway? And then there's a question, well, which parts of the math are supposed to correspond to the world? Because we have what we call gauge degrees of freedom in the description, where the idea is I can change the mathematical description, but it doesn't change what it's saying about the physical world, because those don't correspond to physical degrees of freedom. So I think the project of mathematical physics has succeeded, certainly in terms of prediction and control, so astoundingly well that we have good reason to believe the general project of mathematical physics can work and can work all the way to the end. I mean, this is when people talk about, I want to be able to write on a t-shirt the fundamental equation that describes all of physics. Now, you'd have to understand the math in which that's written, and you have to understand how that math is being used and so on. I still think that could work. I haven't given up on that, and that only works if the world is a certain way. We can't make it that way, right? We don't decide whether the world is mathematically describable.
But could that be an underdetermined problem in the sense that there could be multiple solutions, multiple theories that would all give the same answer, and yet somehow they're really fundamentally radically different?
Well, there certainly could, well, again, let's divide that into a couple questions. Could there be different theories that make all the same empirical predictions? Answer, sure.
Sure. Just add some other stuff.
You know, we know we can do that.
Right.
Typically, the kind of trivial ways of doing that are such that it's clear that one theory is hoked up and artificial and the other isn't. And if you had to choose between them, you'd say, well, the choice is not empirical, but still, we have really good reasons to believe this one rather than that one.
Yes.
So now the question comes, could there be two equally plausible looking, kind of simple, natural looking theories that are nonetheless different theories? They make very different, you know, fundamental postulates, but make all the same empirical predictions. That's certainly logically possible.
Yeah. I mean, when we reached the aliens at some point who've gone on a radically different trajectory, and maybe they're smarter than we are or equally smart, and they've got their t-shirt in principle could use different ideas, different ontology, what's real, different dynamical equations, if that's even the structure, and yet it might be as good as anything that we have.
In a certain kind of principle. That is, I can't rule it out, but I don't think you can rule it in that that's possible.
Sure.
Right? It may very well be that the actual physical structure of the world is such that there's essentially only one simple mathematical structure that will give you all the right predictions. I can't rule it out, but I have no reason to believe it. I mean, I would assume the aliens went through Newtonian dynamics and went through Maxwellian electrodynamics, right? I mean, it seems like a natural conceptual progression.
Unless the thing that I always wonder about, if their senses somehow are so radically different from ours that they engage with the world so differently that the things that seem so natural to us, like gravity, electricity, magnetism, could it be that...
This one I don't have any sympathy with. The aliens are going to stumble over that table just as well as we will, right? I mean, their senses have to present the world at macroscopic scale, pretty much like ours, if they're going to survive in it.
I'm sympathetic to that too, but I can also imagine that we may be sensitive to a slice through reality. And what's amazing is that our slice is coherent and self-contained, and if they have a different slice through reality.
But of course, we've expanded through our instrumentation. I mean, just take the visual spectrum, right? We are naturally only sensitive to a very small slice, literally,
because
of the electromagnetic spectrum.
Because of where the sun spectrum is, basically.
But now with our instruments, right, we are sensitive, using our instruments, to the entirety of it. So our natural, it's true, our kind of natural, unaided awareness of the world is limited, but we've managed through technology to expand that. And to imagine that there's kind of, how could there be an entirely different world we're not touching at all, and they're in contact with, I mean, I don't even see how that's possible.
Yeah, I certainly see how it's possible, but I think it's extraordinarily unlikely.
Yeah, it's logically possible, but it's not something I'm going to stay up at night worrying about.
That I certainly agree with. Well, this has been a fascinating conversation. Thank you so much for coming.
It's been fun.
Thank you for watching.